Welcome! Today we'll explore the relationship between Faraday's law and Lenz's law, two fundamental principles that govern electromagnetic induction. Let's start with Faraday's law. Faraday's law states that the induced electromotive force, or EMF, in a closed loop is equal to the negative rate of change of magnetic flux through the loop. This can be expressed mathematically as EMF equals negative d phi b over dt, where EMF is the induced electromotive force and phi b is the magnetic flux. Before we proceed, let's understand what magnetic flux means. Magnetic flux is a measure of the amount of magnetic field passing through a given area. It's defined as phi b equals b times a times cosine theta, where b is the magnetic field strength, a is the area of the loop, and theta is the angle between the magnetic field and the normal to the area. Now, let's move on to Lenz's law. Lenz's law gives us the direction of the induced EMF and current. It states that the induced current will flow in such a direction that its magnetic field opposes the change in magnetic flux that produced it. This is nature's way of opposing changes, a fundamental principle of electromagnetism. Let's visualize this with an example. Imagine we have a conducting loop and a bar magnet. When I move the north pole of the magnet toward the loop, the magnetic flux through the loop increases. According to Faraday's law, this change in flux induces an EMF. And according to Lenz's law, the induced current creates its own magnetic field that opposes the increase in the external field. So the loop creates a north pole facing the approaching magnet, causing a repulsive force. Now, let's see what happens when I pull the magnet away. As the magnet moves away, the magnetic flux through the loop decreases. Again, this change induces an EMF according to Faraday's law. But now, according to Lenz's law, the induced current creates a magnetic field that opposes this decrease. So the loop creates a south pole facing the retreating north pole, causing an attractive force that tries to prevent the magnet from moving away. Now, let's understand the relationship between Faraday's law and Lenz's law. Faraday's law gives us the magnitude of the induced EMF, which is proportional to the rate of change of magnetic flux. Lenz's law gives us the direction of this induced EMF and the resulting current. The negative sign in Faraday's formula, EMF equals negative d phi b over dt, is actually a mathematical expression of Lenz's law. This negative sign ensures that the induced EMF always acts to oppose the change in flux that produced it. It's important to understand why Lenz's law exists. Lenz's law is actually a consequence of the conservation of energy. If the induced current were to flow in a direction that reinforced the change in flux, we would have a runaway process that would create unlimited energy, which would violate the first law of thermodynamics. Let's look at some real-world applications of these laws. Electric generators use Faraday's and Lenz's laws to convert mechanical energy into electrical energy. Transformers use these principles to step up or step down voltages in our power grid. Even induction cooktops use electromagnetic induction to heat your pans directly without heating the cooktop surface. To summarize, Faraday's law tells us that the induced EMF equals the negative rate of change of magnetic flux. Lenz's law tells us that the induced current flows in a direction to create a magnetic field that opposes the change in flux. The negative sign in Faraday's law is the mathematical representation of Lenz's law. Together, these laws completely describe electromagnetic induction, a phenomenon that powers much of our modern world. Thank you for watching this explanation of Faraday's law and Lenz's law. Understanding these principles is crucial for anyone studying electromagnetism and electrical engineering.